This is SpaceTime, Series 22, Episode 69. Coming up on SpaceTime, towering bubbles of energy discovered at the galactic center, a newly discovered interstellar visitor, and scientists measure the exact size of the proton. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have discovered a pair of enormous radio-emitting bubbles towering hundreds of light years above and below the center of our Milky Way galaxy. The massive features, reported in the journal Nature, are among the largest structures ever observed near the galactic center. The hourglass-shaped feature, which dwarfs all other radio structures in the region, is most likely the result of a gigantic energy burst that would have erupted millions of years ago near Sagittarius A star, the supermassive black hole at the center of the galaxy. The study's lead author, Ian Hayward from the University of Oxford, says the center of the Milky Way is relatively calm when compared to other galaxies with very active central black holes. Even so, from time to time Sagittarius A star can become uncharacteristically active, flaring up as it periodically devours clouds of gas and dust. It's possible one such feeding frenzy triggered powerful outbursts that inflated this previously unseen feature. Hayward and colleagues mapped out broad regions at the center of the galaxy using the South African Radio Astronomy Observatory's Meerkat telescope, one of the precursors to the Square Kilometre Array project. They conducted their observations at wavelengths near 23 centimeters, looking for radio emissions generated by synchrotron radiation. That's produced by electrons moving at close to the speed of light, interacting with powerful magnetic fields. This produces a characteristic radio signal that can then be used to trace energetic regions in space. This radio light easily penetrates the dense clouds of gas and dust that block visible light from the galactic center. By examining the nearly identical size and shape of these twin bubbles, the authors think they found convincing evidence that these features were formed from a violent eruption that over a short period of time punched through the interstellar medium in opposite directions. Study co-author William Carnton from the National Radio Astronomy Observatory in Virginia says the shape and symmetry of the emissions strongly suggests that a staggeringly powerful event happened a few million years ago very near Sagittarius A star. The eruption was probably triggered either by vast amounts of interstellar gas falling onto the black hole, or alternatively by a massive burst of star formation which sent shockwaves careening through the galactic center. The environment surrounding the black hole at the center of the Milky Way is vastly different from the environment elsewhere in the galaxy, and in many ways it remains a region of mysteries. We've already seen evidence of massive gamma-ray bubbles extending thousands of light years above and below the galactic plane. They appear to also originate from Sagittarius A star, possibly generated during a more violent time in the galaxy's past, millions if not billions of years ago. And there are also long narrow filaments found nowhere else, the origins of which have remained an unsolved puzzle since their discovery 35 years ago. The filaments appear as radio structures tens of light years long and approximately a light year wide. Radio bubbles discovered by Meerkat now shed light on the origin of the filaments, with almost all of the more than 100 filaments confined to within the radio bubbles. The authors suggest that the close association of the filaments with the bubbles implies that the energetic event that created the radio bubbles is also responsible for accelerating the electrons required to produce the radio emissions from the magnetized filaments. The amazing thing is these enormous bubbles have until now simply been hidden by the glare of the extremely bright radio emissions coming from the center of the galaxy. Teasing out the bubbles from the background noise has allowed scientists to witness a manifestation of galactic-scale outbursts of matter and energy, ultimately governed by the supermassive black hole at the heart of the galaxy. I'm Stuart Gary. This is SpaceTime. Well, it looks like astronomers may have detected another interstellar comet. The newly discovered object, designated as C2019 Q4 Borisov, was discovered by Gennady Borisov at the MARGO observatory in the Crimea on August the 30th. If confirmed, it'll be only the second such object detected, the first being the flat elongated Oumuamua, which was confirmed in October 2017. Unlike Oumuamua, which was only detected after it made its closest approach to the Earth and was already heading out of the solar system, this new comet is still inward bound, heading towards the Sun. However, from our point of view, it will remain further away than the orbit of Mars, and will come no closer to the Earth than about 300 million kilometres, that's twice the distance to the Sun. Observations indicate the comet's nucleus is somewhere between 2 and 16 kilometres in diameter. C2019 Q4 is currently 420 million kilometres from the Sun. It'll reach its closest point to the Sun, perihelion, on December the 8th, at a distance of about 300 million kilometres. Before that, on October the 26th, it'll pass through the ecliptic plane. That's the plane which the Earth and other planets in the solar system orbit around the Sun. It'll come down from above at roughly a 40-degree angle. It'll then swoop around the Sun before heading off back into interstellar space. After its initial detection, scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, flagged the object as possibly being interstellar in origin. David Finocchier from NASA's Center for Near-Earth Object Studies at JPL worked with astronomers and the European Space Agency's Near-Earth Objects Coordination Center to obtain additional observations. He then worked with NASA's Minor Planets Center in Cambridge, Massachusetts, in order to estimate the comet's precise trajectory and determine whether it originated from within our solar system or whether it's come from elsewhere in the galaxy. The comet's current velocity is high, around 50,000 kilometers per hour, which is well above the typical velocities of objects orbiting the Sun at that distance. The speed indicates not only that the object likely originated from outside our solar system, but also that after swooping around the Sun it will leave and head back into interstellar space. C2019 Q4 was established as being cometary in its nature due to its fuzzy appearance, which indicates the object is a central icy body and is producing a surrounding cloud or coma of dust and gas particles as it approaches the Sun and heats up. Now, as seen from Earth, its location in the sky places it near the Sun. That's an area of the sky not usually scanned by large ground-based asteroid surveys, or for that matter by NASA's asteroid hunting NEOI spacecraft. Problem is, with most astronomical equipment looking directly at the Sun will damage the technology. Astronomers say the object should peak in brightness in mid-December and then continue to be observable with moderate-sized telescopes until about April next year. After that, it'll only be observable with large professional telescopes through to around October 2020. Meanwhile, astronomers will continue to collect observations to further characterize the comet's physical properties and to try and better identify its trajectory. We'll keep you informed. You're listening to Space Time. I'm Stuart Gary. From time to time, we get inquiries from our listeners asking how they can support our show. And that's why we've set up a Patreon account. For just a few dollars a month, you'll get access to a slick commercial-free double-episode version of the show each week, as well as bonus audio content not included in the regular show, plus other rewards like an invitation to join our special patron-only Facebook group. You can get all the details at Patreon, spelled Patreon, patreon.com/spacetime with Stuart Gary, where you can see the various reward levels available and what works for you. And of course, you'll have the satisfaction of knowing that you're helping us develop our show into the future. That URL again, patreon.com/spacetime with Stuart Gary. And you can find all the details in the show notes, or just click the orange button on our website. And thanks to all our patrons, because it's your generosity and support that helps keep our show going. Astronomers are able to classify galaxies according to their physical properties rather than just any human interpretation of a galaxy's appearance, thanks to a technique called Integral Field Spectroscopy. For more than 200 years, telescopes have been capable of observing galaxies beyond our own galaxy, the Milky Way. Only a few were visible to begin with. But as telescopes became more powerful, more galaxies were discovered, making it crucial for astronomers to come up with some sort of way to consistently group different types of galaxies together. In 1926, astronomer Edwin Hubble refined a system that classified galaxies into categories of spiral, elliptical, lenticular, or irregular shape. The system, known as the Hubble sequence or the Hubble tuning fork, is still the most common way of classifying galaxies today. Despite its success, the criteria on which the Hubble scheme is based are largely subjective and only indirectly relate to the actual physical properties of the galaxies themselves. It's a case of what we see rather than what's actually there. Now, all this has significantly hampered attempts to identify the evolutionary pathways followed by different types of galaxies as they slowly change and evolve over billions of years. And that's where Dr. Luca Cortez and his colleagues from the University of Western Australia node of the International Centre for Radio Astronomy Research come in. They used integral field spectroscopy to quantify how gas and stars move within galaxies and reinterpret the Hubble tuning fork as a physically based two-dimensional classification system. Cortez says the world's premier astronomical facilities are now producing surveys consisting of hundreds of thousands of galaxies, rather than the hundreds that Edwin Hubble and his contemporaries were working with. See, astronomers need to classify galaxies consistently using instruments that measure physical properties, rather than a time-consuming and subjective technique involving human interpretation. Cortez and colleagues used integral field spectroscopy to develop detailed maps of the distribution and velocities of different components within galaxies. Then, using this information, they were able to determine the overall angular momentum of a galaxy, which is the key physical quantity affecting how a galaxy will evolve over billions of years. Their study involved some 488 galaxies observed by the 3.9-metre Anglo-Australian telescope using an instrument called SAMI, the Sydney AAO Multi-Object Integral Field Spectrograph. The SAMI project, led by the University of Sydney and Castro, aims to create one of the first large-scale resolved surveys of galaxies, measuring the velocity and distribution of gas and stars of different ages in thousands of systems. Cortez says the hope is to identify the physical triggers that cause one type of galaxy to evolve into another.
Our main classification scheme is something that has been around for almost 100 years. And this is something that was based exactly on what was possible 100 years ago. So a simple photographic plate image where you look at the shape of a galaxy and you figure out that galaxies come in very different shapes. So you have round galaxies that have elliptical shapes, and then they are called ellipticals. Then you have galaxies that have a completely different shape. They look like disks with spiral arms, and this is where the name spirals come from. And then the astronomers realized that there are intermediate classes where you have a disk morphology, but there are arms, the spiral arms fade a little bit, and this is what we generally call lenticulars. And this has been the main, let's say, classification scheme that we have been using, astronomers have been using for almost a century, as I said. And it has been very powerful. The limitation is that since it was based 100 years ago, this is mainly a visual classification, and it's very indirect links to the physical properties of galaxies.
Now we understand their evolution a lot better, and you've been looking at all those factors combined with an overall better understanding of the way galaxies were 12 billion years ago compared to what they are like now to reinterpret that.
Yeah, pretty much. There's been a lot of progress, both from the instrumentational point of view and also consequently from our understanding of how galaxies evolve. And what we have realized in the last decades is that, of course, the basis of the Hubble classification give us information about two kinds of what can we call transformation of galaxies, or the way galaxies evolve. On one side, we have a variation in the star formation activity. We know now that the stars are forming the spiral arms, and so when we reduce the star formation activity, the spiral arms fades, and this is why, for example, in many cases, a spiral can kind of look like more an lenticular galaxy. On the other side, however, we also know that ellipticals are not different from spirals only from the star formation activity, but also in terms of the orbits of stars. In spiral stars have clear orbits, so they rotate around the center. In ellipticals, stars have more random orbits. And this, of course, is something completely different from the activity of star formation of galaxies. And so now we can finally discriminate between a change in star formation activity and a change in structural properties. And this has been the key for the, let's say, the new analysis that have been done, where we've been able to show that the, let's say, great part of the variation in the morphology of galaxies actually comes from a variation in structure.
And so by looking at how gas and stars are actually moving within a galaxy, that tells you a lot about the true characteristics of that galaxy, doesn't it?
Correct, yes. Now that with new technology we are finally able to pretty much reconstruct how stars and gas move around within the gravitational potential of a galaxy, we are able to determine not only whether stars are rotating or they follow random orbits, but also how fast they are rotating. And so this is pretty important to figure out what are the kinematical properties of galaxies that they regulate in one way how galaxies look like today.
And that's where the multi-object integral field spectrograph, SAMI, comes in.
Correct, yes. This has been the key because until a few years ago, spectroscopy has been around in astronomy for more than a century, and previously what we were able to do is just to put a single fiber on a galaxy and to get just how the galaxies was moving with respect to us, so whether it was approaching to us or it was going away from from us. We didn't have any clear information about the, let's say, the kinematics of the stars and gas with respect to the center of the galaxy. With SAMI, we are able to put, in this case, it's around 61 fibers in different parts of the galaxy, so we get an independent estimate of the velocity of stars and gas in each part, and we can reconstruct what in astronomy we call a velocity field to figure out how fast, whether the stars are rotating or not, and if they are rotating, how fast they are rotating.
And when you do this, does this tell you something about what the building blocks of galaxies are as well? I mean, for a long time, we were assuming that it was just globular clusters coming together to form the seeds of galaxies. Then we realized galaxies collide with each other and that they grow by merging and other interactions like that. For example, the Large Magellanic Cloud, it looks like it's been pretty badly beaten up. So there's a lot of gravitational interactions going on.
Yeah, definitely. I mean, this in itself, it doesn't provide us a direct, let's say, information about how galaxies evolve, but then the spread in, let's say, rotational velocities, the balance between galaxies that are in which the stars are rotating and in which the stars have random motions, give us what strong constraint to our different theories of galaxy formation, because then we can go to supercomputers, test different scenarios, and figure out whether different scenarios are able to reproduce the observations today, or whether we can discriminate, let's say, some possibilities. So these data definitely provide a strong constraint and add to different other constraints also for different observations to have a better picture of what are the building blocks of galaxies.
How much can we rely on dark matter's contribution towards galaxy evolution? I understand that dark matter makes up something like 80% of the matter within surrounding a galaxy in the halo. How does that affect the way galaxies evolve? Do we know much about that, other than its gravitational influence?
Well, we again, observationally, what we can trace is just indirectly the distribution of dark matter and how it affects, let's say, the gravitational potential of galaxies, because, of course, it's dark, we cannot detect it. But then it's really critical because, again, with the numerical simulations, what we can do is we can see what would happen to, let's say, throughout the age of the universe to galaxies if we remove dark matter artificially and see how they would evolve and if we have dark matter. And dark matter turns out to be really critical simply because it increases the masses, the potential well where the gas and stars are formed and are stored, and so make it possible throughout the age of the universe to allow galaxies to form rapidly. And we can explain in this way the plethora of different types of galaxies that we see, because without dark matter, galaxy evolution would have been significantly slower and less efficient.
That's Dr. Luca Cortez from the University of Western Australia and the International Centre for Radio Astronomy Research. I'm Stuart Gary. You're listening to SpaceTime. Physicists have carried out the most precise measurement of the size of a proton ever undertaken, finding it to be smaller than expected. The new measurement places the size of the proton at 0.833 femtometers, which is just under a trillionth of a millimeter. This measurement's around 5% smaller than the best previously accepted radius value. The proton consists of 2 up and 1 down quarks, held together by gluons, and usually located in the nucleus of an atom. Protons have a positive charge, and they're surrounded by a sea of electrons, which are negatively charged. And usually they're also accompanied in the nucleus of an atom by neutrons. It's the number of protons in the atom which tell you what chemical element that particular atom is. The new findings reported in the journal Science represents a crucial step towards solving a mystery that's preoccupied scientists around the world for the past decade. Prior to 2010, scientists thought they had a pretty good idea of the size of a proton. But then in 2010 that changed when a team of physicists measured the proton radius value to be 4% smaller than what was expected, and that confused the heck out of the scientific community. Since then, the world's physicists have been scrambling to resolve the proton radius puzzle, as they call it, the inconsistency between these two proton radius values. This puzzle has been an important unresolved problem in fundamental physics today. The study's lead author, Professor Eric Hessels from York University, says the level of precision required to determine the proton size made this the most difficult measurement his laboratory has ever attempted. Hessels and colleagues spent 8 years using a new electron-based measurement system to determine how far the proton's positive charge extends. The quest to resolve the proton radius puzzle has far-reaching consequences for understanding the laws of physics, such as the theory of quantum electrodynamics, which describes how light and matter interact. 3 previous studies were pivotal in attempting to resolve the discrepancy between electron-based and muon-based determinations of proton size. The 2010 study was the first to use muonic hydrogen to determine the proton size, compared to previous experiments using regular hydrogen. At that time, scientists studied an exotic atom in which the electron was replaced by a muon, the electron's heavier cousin. Then a 2017 study using hydrogen agreed with the 2010 muon-based determination of the proton charge radius, while a 2018 experiment also using hydrogen supported an earlier pre-2010 value. Hessels and colleagues wanted to both resolve the proton radius puzzle and also understand why the proton radius took on a different value when measured with muons rather than electrons. The York University team studied atomic hydrogen to understand the deviant value obtained from muonic hydrogen. They conducted a high-precision measurement using a frequency offset separated oscillatory fields technique, which they developed for the experiment. Their measurement used a fast beam of hydrogen atoms created by passing protons through a molecular hydrogen gas target. The method allowed them to make an electron-based measurement of the proton radius that was directly analogous to the muon-based measurement from the 2010 study. I'm Stuart Gary. You're listening to SpaceTime. The world's most advanced military telecommunications satellite has successfully been launched and placed into geostationary orbit. The Advanced Extremely High Frequency, or AEHF-5 satellite, was launched aboard a United Launch Alliance Atlas V rocket from Space Launch Complex 41 at the Cape Canaveral Air Force Station in Florida. The Atlas V was flown at its most powerful 551 configuration for the mission, equipped with 5 strap-on solid rocket boosters.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2. We have ignition, and we have liftoff of the United Launch Alliance Atlas V rocket with AEHF-5 for the United States Air Force Space and Missile Systems Center.
Vehicle throttling down to 67% thrust. Engine response looks good, and PU system has gone to closed loop control as expected. System response looks good. RD-180 engine operating parameters look good. Mach 1 Atlas V is now supersonic. RD-180 continuing to look good. Now passing through max Q, and engine throttling back up to 94% thrust. RD-180 engine operating parameters look good. Seeing good chamber pressure on all 5 SRBs, good symmetric burn. It's passing 1 minute now into flight. RD-180 continuing to look good. Also seeing good chamber pressure across all 5 SRBs. Engine now throttling down to 75% thrust as expected. Engine response looks good. Standing by for SRB burnout shortly. And we're seeing burnout on all 5 SRBs. Engine back up to full thrust. Standing by for SRB jettison. And we have good indication of jettison of all 5 solid rocket boosters. 1 minute 50 seconds into flight. Vehicle's gone to closed loop guidance. Atlas V is now 38 miles in altitude, 48 miles downrange distance, traveling at 4,700 miles per hour. Vehicle body rates looking good. Engine now throttling to maintain 2.5 G acceleration limit. Engine response and vehicle body rate response looks good. RCS pyro valve has been fired. Reaction control system is pressurizing to flight levels. Now coming up on 3 minutes into flight. RD-180 pump speeds and injector pressures continue to look good as it's maintaining that throttle limiting. Vehicle body rates continue to look good. Standing by for payload fairing jettison. And we have good indication of payload fairing jettison and CFLR jettison complete as well. Vehicle now throttling back up to 95% thrust. Engine response looks good. Engine is now throttling to maintain 4.6 G acceleration limit. Engine response looks good. Now passing 4 minutes into flight. Centaur has begun the boost phase chill down sequence. RD-180 engine continues to look good as it maintains that 4.6 G throttle acceleration limit. 4 minutes 15 seconds in. Standing by for BECO shortly. And we have BECO booster engine cutoff. Standing by for stage step. And we have good indication of Atlas Centaur separation. We have pre-start on the RL-10, standing by for ignition. We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good. First burn of today's mission will last approximately 7 minutes. Now at 5 minutes into flight, the Centaur is 110 miles in altitude, 500 miles downrange distance, traveling at 13,900 miles per hour. RL-10 chamber pressure continues to look good. Vehicle body rates also maintaining good values.
This is the fifth of 6 AEHF satellites being built for the constellation, providing highly secure jam-proof connectivity for the US Air Force, as well as allied nations who contributed to the project, including Australia, the United Kingdom, Canada and the Netherlands. Each of the 6,168 kilogram satellites are based on the Lockheed Martin A2100M platform, providing greater capacity than the entire Milstar constellation it will eventually replace, and carrying enough fuel to remain operational for at least 14 years. Well, just weeks after the United Launch Alliance Atlas V mission, another United Launch Alliance rocket, this time a Delta IV, blasted into orbit carrying the second of a new generation of Global Positioning System satellites. The United States Air Force GPS-3 Magellan satellite flew off Space Launch Complex 37 at the Cape Canaveral Air Force Station in Florida, marking the 29th and final flight of the Delta IV rocket in its medium configuration.
Roll for ignition.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, we have ignition and liftoff of the United Launch Alliance Delta IV rocket carrying the GPS-3 Magellan mission for the United States Air Force Space and Missile Systems Center.
Body rate response looks good.
You are hearing the voice of Patrick Moore providing launch
Main engine
vehicle
chamber pressure
data.
looks good. Seeing good chamber pressure across both SRMs. 25 seconds into flight. Good operating parameters on the R68A main engine. Chamber pressure on both SRMs continues to look good. Good body rates on the vehicle. Vehicle is now passing Mach 1. Delta IV is now supersonic. Main engine continuing to perform well, continuing to see a good burn profile on both SRMs, and vehicle is now passing through max Q, maximum dynamic pressure. Main engine continuing to perform well, continuing to see good SRM chamber pressure profiles. 1 minute 15 seconds into flight. Approximately 15 seconds remaining till SRM burnout, and we have burnout on both SRMs, standing by for separation. And we have separation of both solid rocket motors. Vehicle is now going to closed loop guidance. Body rate response looks good. Seeing minor correction in the roll attitude as expected. And the Delta IV rocket now weighs just 1/2 of its liftoff weight. Second stage ACS system pressurization valve has been opened. RCS pressure response looks good. Now 2 minutes 5 seconds into flight. And vehicle is now passing through Mach 5. Delta IV is now 36 miles in altitude, 55 miles downrange distance, traveling at 4,760 miles per hour. Chamber pressure on the R68A main engine continues to look good. Body rate responses also continue to look good. And upper stage lock system has begun the boost phase chill down sequence to begin thermal conditioning of the upper stage engine. Now less than 1 minute remaining in the first stage phase of flight. And upper stage fuel system has begun boost phase chill down. Now 3 minutes 15 seconds into flight. Delta IV is now 65 miles in altitude, 148 miles downrange distance, traveling at 8,500 miles per hour. Now passing 3 minutes 30 seconds into flight. Main engine continues to perform well. Chamber pressure looks good. Body rate responses on the Delta IV also look good. About 10 seconds remaining until booster throttle down. And booster's now throttling down to the minimum power level in preparation for BECO, standing by for BECO. And we have BECO booster engine cutoff, standing by for stage separation. We have good indication of stage separation. The upper stage engine nozzle extension is deploying. We have pre-start on the RL-10, standing by for ignition. We have ignition and full thrust on the RL-10 engine. Chamber pressure looks good. Body rates look good. Standing by for payload fairing jet. And we have payload fairing jettison.
To mission control at T plus 4.5 minutes. We've just heard Patrick Moore report the successful execution of the early events of today's flight, and all systems continue to operate nominally. The Delta IV second stage and GPS-3 satellite are traveling in a northeasterly direction up the U.S. eastern seaboard. This mission is now in the first of 2 planned RL-10 engine burns. This burn will last approximately 9 minutes.
With the final flight of the Delta IV Medium and the Titan family of rockets long retired, only the Delta IV Heavy and Atlas V remain on the United Launch Alliance manifest, as the company continues its transition towards the new Vulcan Centaur launch system, expected to begin flying in 2021. This launch also marked the 73rd flight of a GPS satellite. The Lockheed Martin-developed GPS-3 system is designed to provide improved navigation accuracy for the US military and its allies, with better anti-jam resistancy and also a new signal for civilian users. The 4,400 kilogram satellite provides precise positioning, navigation and timing, or PNT information, down to just 50 centimeters. The GPS-3 signal is also compatible with Europe's Galileo satellite navigation system. At present, the Global Positioning System network features 31 operational satellites orbiting the planet at an altitude of around 20,200 kilometers. The United Launch Alliance's next mission will be the unmanned orbital test flight of Boeing's new CST-100 Starliner capsule, which will be aboard an Atlas V rocket using Space Launch Complex 41 at Cape Canaveral. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. A new study warns that mint-flavoured e-cigarettes could be a cancer trigger. A report in the Journal of the American Medical Association claims mint and menthol-flavoured e-cigarette liquids contain a carcinogenic substance called fugon, which has been banned as a food additive. The problem is, it seems the legislation hasn't caught up with the science yet. And while it is banned as a carcinogenic additive for food, it's not banned as an inhalant. Fugon is a constituent of oil extracts prepared from mint plants, including peppermint, spearmint, and pennyroyal. New research presented at the annual meeting of the European Association for the Study of Diabetes suggests that a 16-week vegan diet could boost gut microbes related to improving body weight, body composition, and blood sugar control. The study included 147 overweight people with no history of diabetes who were either put on a low-fat vegan diet or asked not to change their diet at all. Researchers found those in the vegan group experienced changes in their gut bacteria, their microbiome, and this resulted in an average weight loss of 5.8 kilograms, especially in fat around the gut. And just as importantly, it also improved the body's insulin sensitivity. A new study warns that clods of weathered crude oil originating from the 2010 BP Deepwater Horizon catastrophe could remain buried in sandy Gulf Coast beaches for decades. The findings by scientists at Florida State University warns that these large clumps of oil and sand, known as sediment oil agglomerates, will take at least 30 years to decompose. The research, published in the journal Scientific Reports, reveals that these golf ball-sized oily clods contain substances that are highly harmful to both the environment and humans. Oil and other pollutants from BP's Deepwater Horizon spill contaminated an estimated 965 kilometres of sandy beaches along the Gulf of Mexico coastline. Scientists have discovered a new species of electric eel which produces the highest voltage discharge of any known animal. A report in the journal Nature says the eel, part of the naked-back knifefishes group, native to South America and Mexico, produces an electric shock of up to 860 volts. Electric eels, which can reach 2.5 metres in length, are more closely related to catfish and carp than to other eel families. And speaking of eels, scientists have found a significant amount of eel DNA in Loch Ness. That's the key finding of research by scientists from the University of Otago looking at the total environmental DNA, or eDNA as it's called, present in Scotland's famous Loch Ness. The large freshwater lake is best known for the thousands of reported sightings since the 6th century of a mysterious long-necked plesiosaur-like monster. Researchers collected over 250 samples of water from various spots across Loch Ness. eDNA from each sample was captured, extracted and sequenced, then compared against genome databases to reveal a comprehensive picture of life present in the lake, examining bacteria, the fish, and pretty well everything in between. They found no DNA evidence supporting any monster hypothesis. They also found no DNA evidence supporting some other ideas used to explain the Loch Ness monster. There was no DNA from giant catfish, no DNA from sturgeons, and no DNA from Greenland sharks. But one popular theory, that Nessie's actually a giant eel, couldn't be disputed, as a very significant amount of eel DNA was found. Apple has finally released its latest iPhones as the battle for the hearts and minds of cell phone users around the world reaches new technological highs. As we predicted a couple of weeks ago, there will be 3 new devices available. There'll be an iPhone 11, an iPhone 11 Pro, and an iPhone 11 Pro Max, although that'll set you back around $2,500. The iPhone 11 Pro and iPhone 11 Pro Max are the successors to last year's iPhone XS. They feature a stainless steel body, 3 rear-facing cameras, and an OLED display. And speaking of display, the bad news is the notch is still there. The cheaper alternative will be the new iPhone 11. It features an aluminum body with dual rear-facing cameras and a lower resolution LCD display. With all the details, we're joined by Alex Horosh from whistleout.com.au.
I guess you'd probably call the iPhone 11 the new default iPhone. It's a direct successor to the iPhone XR from last year, and it's pretty similar. It's got a faster processor, but it's still got a 6.1-inch LCD screen. It's got 2 rear cameras on the back now, and it's still made from aluminium rather than stainless steel. So that's $1,200 for the 64-gigabyte model. Yeah, it's just, I guess, the iPhone you buy if you don't want to spend larger amount of money because the iPhone 11 Pro and it starts at $1,749, and then the Pro Max is more expensive again at $1,899. So they're quite pricey and a little bit more expensive than last year.
And if you want the Pro Max with the big memory, that's going to be $2,500.
Yeah, that's for the 512 gigabyte model, which is kind of crazy. It's a lot of money to spend on a phone. And I think most people don't need the 512 gigabyte model because, I mean, at the end of the day, they're phones. So the most interesting things about the Pro is that they've got 3 rear-facing cameras, which is something that I guess Android phones have been doing for a while, but it's the first time Apple has kind of moved into this territory. So you've got a standard wide-angle lens, you've got your zoom lens, but you've also got an ultra-wide-angle lens this time around, which has, I guess, what you'd call a zoom factor of 0.5. So you're kind of like zooming out when compared to the primary lens. And in addition, Apple's added in night mode, similar to what we've seen on smartphones like the Huawei P30 Pro and the Google Pixel. So like in dark environments, night mode can be used to take multiple images over a longer period of time to stitch them together into a brighter photo. The other big change with the iPhone 11 Pros is that they've got much heftier batteries. So Apple is saying that the 11 Pro should get about 4 more hours than the iPhone XS, and the 11 Pro Max should get about 5 more hours than the XS Max. That's pretty decent improvements, and it should put them at the top of the battery pack in terms of iPhones, which is great because iPhones haven't always had the best reputation for battery life, and it seems like Apple has kind of stopped sacrificing battery for the sake of a thinner phone because their devices are just a little bit thicker and just a little bit heavier this time around. But I think, it's a trade-off that's important to make because battery life is so important.
That's Alex Horosh from whistleout.com.au. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through Apple Podcasts, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audioboom, from spacetimewithstuartgary.com, or from your favorite podcast download provider. SpaceTime is also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and around the world on iHeartRadio and TuneIn Radio. If you want more space time, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web that I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTime with Stuart Gary on Instagram. On Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary, and you can also find us on the SpaceTime with Stuart Gary YouTube channel. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
If you want more space time, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, @SpaceTime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary.